Okay, there are two types of reactions that are very common. One is called single replacement, the other is called double replacement. Now, with single replacement reactions, you have to understand something called oxidation and reduction. Okay, so oxidation is the loss of electrons. Okay, so when that element loses an electron, it becomes more positive. So if we were looking at something like silver and put a little zero at the top to indicate it's a metal. Some instructors do that. Some textbooks do that. Some don't. I always do. So you know for sure it's an element. Okay, it's a metal, basically. Okay, so if we were to lose, and you can lose 1, 2, and 3 electrons, any number. So in this case, silver likes to form a +1 ion. When there's the loss of that electron. Now, this is called a half reaction, where it shows the loss of an electron. Now, if this is a half reaction, there must be another half to go with it, right? That's called, there's a handout here. Okay, reduction's the opposite of oxidation. So oxidation, you lose an electron. Reduction means you accept it. Okay, so that's another type of half reaction. So we have losing and gaining, and they have to happen together, no exceptions. When one electron is freed up, it's got to go someplace. If it doesn't go anyplace, it's called beta radiation, which is very bad. So there's always something to accept that electron that's being transferred. Now, the only way this is going to happen is why? What do we say when we talk about chemistry reactions? Stability. If losing an electron is not stable, it won't happen. So in an oxidation reduction reaction, you have to have something that's becoming more stable if it loses an electron, and something that's more stable if it gains an electron. So what we're going to do now is we're going to put these two together. Now notice how many electrons on the top here on the oxidation am I losing? 1. How many is this iron cation down the bottom receiving? 2. So those have to match. Electrons given off have to be equal electrons being received. So when we put these two reactions together, and then algebraically, I add them together. Let's see, let me, need more room here. Now, do you see a problem with that? On the right side, in the correct side. So the silver is giving up an electron right here on the top. That silver is giving up 1 electron. On the bottom, iron is receiving 2 electrons. What's going on here? Is there okay, yeah. The iron needs to receive 2, right? So how can we fix this? Yeah, we can do that by doubling the whole thing. Think of this as an algebraic equation. So what we're going to do is going to have, instead of 1 silver, we're going to have 2 silvers. Now, we give off 2 electrons, we receive 2 electrons. They've always got to match. Always, no exception, always got to match. So what you can do is you multiply each equation by some number to up, because you're looking for the electrons to match. So whatever you have to do, multiplying either the one that gives off electrons or the one that receives electrons, you fiddle with that till a number of electrons match. So if we were to algebraically add these two, the electrons cancel. So this is the reaction. Now, if we didn't have 2 electrons on the top and bottom, they wouldn't cancel. So this you have to memorize. Oxidation, losing electrons.
0 means negative, or it means neutral charge, right?
Exactly. That means it's a metal too.
Metal.
Yeah. Bless you. All right, now your lab this week, your first wet lab is going to have lots of, I sent an email out regarding this, has lots of different chemicals in, and you all need to do first aid on these guys. So we're looking at these here. So make sure you have first aid for those. Okay, now in your lab, what you're going to be doing is you're going to do some reactions. Oh, and by the way, adding, yeah, so the number of electrons match. Multiplication. Then once the electrons match, then you add them up. So first step is to match electrons, and they may already be matched, but just if they're not, match them up by multiplying across the whole thing, and then add them up. So the electrons cancel. Now, usually in a single replacement reaction, you start with a metal and a salt. So in this case, so the salt is going to be the ion, and then the metal is going to be the metal with zero charge. Now, sometimes this works, like I was saying earlier, that we're looking at stability reasons. If the metal going to the cation is more stable than the metal itself, it has to be more stable, otherwise it won't happen. So sometimes when you put these two together, something happens and sometimes nothing happens. That's the goal in your lab. If you're going to be trying all these different combinations and seeing which one works and which one doesn't work. Now, hi, there's a handout here. Wait, stop. Handout here. Okay, that table is a table of stable reactions. Now, the higher in the table it goes, the more stable they are. So this is increasing stability. So lithium at the very top going to lithium cation plus electron is extremely stable. At the bottom, gold going to the gold cation is not very stable at all. So basically, gold wants to stay a metal, and lithium does not want to stay a metal. Because of the way the electrons, his question had to do with why is it more stable? It has to do with how the valence electrons are arranged when we do the electronic configuration. That's what drives its stability. In other words, the lithium really wants to lose an electron. Group 1. So everything in group 1 wants to lose an electron. Group 2 wants to lose 2 electrons. Group 3, up at aluminum, wants to lose 3 electrons. Group 7 wants an electron. Group 6 wants 2 electrons. Group 5 wants 3 electrons. And it has to do with how the electrons are configured when you do the electronic configuration. You know, the 1s2, the 2s2. No, not necessarily. It's just that everything here, group 1 wants to lose an electron because it's more stable once it's gone. The halogens are the opposite. They want an electron to become more stable. So that's why they form a -1 anion.
What does that have to do with this?
Well, if it wants to get rid of an electron, it's going to be more stable if it loses it.
Right, so it's the fewer.
If you're in group 1, 2, or 3. If you're in groups starting with nitrogen, 5, 6, and 7, you're more stable if you gain electrons. Group 1 is on the far left. It wants to gain, or excuse me, wants to lose. Group 4 is a weird. okay? It neither likes to lose electrons or gain electrons, so it doesn't do either. So in other words, it doesn't form an ion with group 4 with a carbon at the top. And then also the noble gases don't form ions either because they're extremely stable. So everything forms ions except for group 4 for carbon and the noble gases, just to summarize. Okay, so this table over here can be used to predict whether this reaction is going to happen or not. So first thing you're going to do is find the relationship between silver and iron in the table. Okay, so there's iron. Oops. There's iron and here's silver. So according to this, iron would rather be an ion than a metal because it's higher than silver. Remember, the higher you are in this table, the more stable you are. That means, according to this, iron likes to get rid of 2 electrons and form an Fe plus 2. Silver wants to lose an electron, but it's lower. It's lower. So iron wins. Higher the table, higher the position in the table, you're more stable. But look at what they are, though. These are all oxidation reactions. So this says, if iron is on the left and higher, it says iron is more stable, iron the metal. Don't forget, these are all metals. So let's look at our reaction over here now. According to that chart, if you find iron on that chart, it's up above the silver. And that chart says that iron wants to become a cation. Well, it's already there. It's already a cation. Okay, the silver down below doesn't want, according to the iron, it's weaker in terms of stability. So iron wins. So this reaction would be no reaction. So what you do, this is the procedure, is you want to net this out. Okay, so first thing you do is find the two elements on the chart. Okay, so we have iron and silver. If the salt is above the metal, the reaction is no visible reaction, or NR. Okay, and the salt, iron +2, is above silver, so no reaction. Yeah. Which part? If a metal can lose electrons and that new ion that's formed is more stable than what you started with, it'll happen.
What will happen?
It'll lose 2 electrons. So if it's not more stable, it won't happen. And it's always compared to something else. So we always have, in a single replacement reaction, we always have a salt and we have a metal. And the question is, where is the salt in relation to that metal? If the salt, in this case, it's iron +2. If the salt is above the metal, nothing happens. Because the salt is more stable than the metal below it.
What makes it salt? Like, isn't iron metal, not a salt?
It is a metal when it's got a charge of 0. It is not a, I mean, it's on the periodic table, it's considered a metal in that group.
Right.
But when it becomes a salt, in other words, a cation, it's no longer a metal.
Okay.
Well, this is a table of everything losing electrons. Okay, we go iron to iron +2 electrons. Okay, now the thing is, because iron wants to lose electrons more than the silver, it should be in an F2 +2 state. And it's already there. That's what we start with. So that means it'd rather not go to the metal because it's more stable the way it is. Yes, exactly. So in your lab, you're going to do all these combinations and you're going to observe. Is something happening? Is a reaction happening? Is there a bubbling, change in color, something like that? And that's the essence of single replacement reaction. It's an oxidation reduction reaction. And they abbreviate that by saying a redox. REDOX, redox. Also, I've got 2 demos I'm going to have going. Oh, in fact, I'm going to run over and get my instructional assistant to start one of them so that by the time we get over there, it'll have progressed. Let me run and do that real fast. I need a favor. Could you start the demo? Did you put the lab together for me today? Okay, there's 2 demos. One is with a copper wire.
I think he has already started it.
No, the other one is really slow. So if you could start that, so by the time my class comes in, it'll progress. And all you do is you wash the steel wool with acid and then dump it in a salt solution, and then it's changes could occur. Thank you. Okay. She's going to start the second demo. Yeah. All right. So let's do another example. Okay, now instead of saying Fe plus 2, I'm saying FeSO4. Because the charge on SO4 is -2 and the iron is +2. So question mark. Will it happen? Well, if it does happen, aluminum what? Say again? You mean on the iron sulfate? Yeah, I've done this for a whole bunch of years, and I just happen to know that, not because of anything else. All right, so the question is, if we take aluminum metal, like aluminum foil, and it's in the presence of ferric sulfate, iron sulfate, will anything happen? In other words, will we end up creating iron metal, and then the aluminum will dissolve. Okay, so what we do now is we need to find these two on the activity chart. So we look on our activity chart and we find aluminum is okay. So there's aluminum and iron. And remember, iron is in the salt, the ionic phase. It's Fe plus 2, not Fe 0. Aluminum is the 0. Okay, so notice aluminum is above the iron. If the salt is below the metal, the reaction happens. Okay. So will this reaction happen? Right. The iron, is that a yes? It will happen? Okay. Yes, you just find what's the salt. Iron's the salt. It's below the aluminum. So that means aluminum wants to become oxidized more than the iron wants to stay oxidized. Yeah. Yeah. So the reaction is going to go because it's more stable than what you from which you started. Okay. It's just you find the salt and the metal on your activity chart. In this case, the iron is below the aluminum, the iron salt. Yeah. Okay, so right, well, you need to be able, number one, find it on the chart and determine which is higher and which is lower. As far as writing the equation, what you're going to do is you don't know what this is yet, right? But you know, on your little droppers, you're gonna have a spot plate and little droppers. And you're gonna drop it, wait 5 minutes and see if anything changes. If nothing happens, it's gonna be a no visible reaction, or NVR. Okay, well then if something does happen, then what might it be? Well, we know that the metal loses electrons, right? So let's write out the two half reactions. Okay, so the aluminum loses 3 electrons. The iron, to become iron metal, has to gain 2 electrons. Okay, now half reactions have to match the number of electrons. So we have a 3 and a 2 deal going here, right? So we have to figure out how to make, what's the common denominator between 2 and 3? 6. So 6 is a good number to shoot for because 2 goes into 6 and 3 goes into 6. So if we multiply this by 3, I need more room. That'll give us our 6 electrons. But we have to multiply this one by 2 to get our 6 electrons. So let's rewrite this now. So it's going to be 2 aluminum metals plus 3 irons gives us 2 aluminum ions plus 3 iron metals. Now I put all the 2s and 3s in there so that the 6 electrons is matched on either side. Okay. All right. Now remember though that we have something called a spectator ion. Now, when I was at that baseball game last week, I was a spectator. Did I ever pick up a ball and hit it? No, I did nothing. So a spectator ion doesn't do anything either. It just kind of goes along for the ride. So the sulfate is the spectator ion here. So we need to put the sulfate back in. So that's going to pair up with the iron and the aluminum. Now the sulfate, it's got a charge of -2. So it's going to be carried along So now it's going to be like that. So the spectator ion, in this case, is sulfate, which is a -2. So this will have a visible change. Either the aluminum will just go away and the iron, and usually iron metal doesn't stay iron metal very long. Usually it forms rust. And the rust isn't orange. The rust is usually dark gray. Now, this is complicated because the aluminum is a +3 and the iron's a +2. So there's some stuff we have to do to get those to match up. All right. So there's a bunch of parts to this. One, you've got to, first of all, locate the atoms in the activity chart and determine whether the reaction will go or not. If it's a go, then you've got to take the salt to the metal and the metal to a salt and make sure your number of electrons balance with the half reactions. That's what we did here. Oops. Now, this happens in nature a lot. Like whenever meteorites used to land, the Native Americans didn't know how to mine iron. So what they did is they found the meteorites with iron embedded in it. And on the outside of the meteorite, the iron rusted. But if they broke the meteorite open, they found pure iron that wasn't rusted. And so they were able to make tools with it. Same with the ancient civilizations, the Egyptians and the Mesopotamians and all those really ancient civilizations, they did the same thing. Gold. Notice where gold is on the activity chart? Way at the bottom, AU, way at the bottom. Means it doesn't like to be oxidized. That's why when you go mining, you frequently find gold metal, nice shiny gold metal. The first nugget that was found up at Sutter's Creek was the size of your fist. Can you imagine finding a nugget that big? What that sucker was worth? Oh my gosh. And they were just walking in the stream and they saw this thing shining with the sun glistening. That big. Of course, it just as well could have been fool's gold, which is just as shiny, but it's iron pyrite as opposed to gold. Okay, so let's do one more. What time is it? Okay, now tomorrow we're doing double replacement. Double replacement doesn't involve any metal at all. That's what we're going to use the solubility table I put together for tomorrow. And then the second wet lab is going to be on double replacement reactions. And again, there's a lot of first aid in both of these. So make sure the first aid is done before you come to class tomorrow and Thursday. Okay, so let's do zinc metal and well, let's do rust instead. Okay. That's not the formula for rust. It's a form of a rust, but it's not the most common one. The reason I'm using this one, the calculations are easier. Okay, so if we throw iron oxide, FeO, and zinc metal together, is anything going to happen? Okay, so step one is find them on your chart. Bless you. Okay, so here's iron. And where's zinc? Zinc is right here. Okay. So which is the salt here? Iron, which is the metal? Zinc. Okay. All right. Find those on a chart. Which is higher? The zinc or iron? Zinc. So the iron salt is below the metal. So if it's below the metal, what happens? So if the salt is above the metal, there's no reaction. So the salt, is it above or below the metal? Metal zinc. Below. Right? So iron is the salt and it's below the metal. So that means the metal wants to oxidize more. So this is a go, this reaction. Okay, that means let's write out the half reaction. So we have zinc metal loses 2 electrons and becomes Z plus 2. The cation part of the salt is Fe plus 2. Now I'm going to add these two up. Notice the electrons balance without playing any games. So those are immediately going to cancel. So we're left with, let's write the metal first. And then what's the spectator ion? Oxygen spectator ion. So it's carried through. So spectator ions are very common. We're going to see these again tomorrow for double replacement reactions. Remember, spectator ions are usually anions, by the way. Sometimes they're cations, sometimes they're anions, but they don't do anything. So they go through unchanged. So this reaction happens. Now in your lab tomorrow and Thursday, you're going to get lots of practice doing this. So, all right. Well, let's do another one. Okay, so we have zinc metal, and we throw some sulfuric acid on it. So what are the possible spectator ions here? Going to be the sulfate again. SO4, spectator ion. And its charge is -2. Okay, so the question is, whenever you have an acid, the acids have an H plus in them. In this case, there are 2 H pluses. In fact, let's, instead of sulfuric, let's simplify this. Let me make it, hydrochloric acid, just has one H. Okay, so hydrogen can be a +1 or -1. When it's an acid, it's always +1. And we haven't talked about acids or bases at all yet, but something that we'll get into in unit 5. So an acid, to be an acid, you have to have an H+ in there. So HCl looks like this. Oops. So the H+ is functioning as a salt now. So if we write the 2 half reactions, we're going to have that's 1/2 reaction. That's the oxidation. Remember, when we lose electrons, oxidation. And then the H+, now notice, find H+ on your activity charts. It's about 1/3 of the way up. Notice it's H2. It's not just plain H, it's H2. So we have to balance this now. Okay, and we've got electrons cancel. Question is, does this reaction happen? Okay, so find the salt, which is H+, and then zinc we've already identified. Zinc is up there. So does this reaction go? Now, on the test, I'm going to give you questions like this, and I'm going to ask you, does this reaction happen? And you're going to have to explain to me whether it doesn't happen or does happen. And it's going to be because of the location of the metal and the salt in the activity chart. Yeah. Yeah, if the metal and salt, what's your relationship? So this is a bell ringer. Sorry. Okay, if the okay, so we have the salt, which is H+, and then we have the metal, zinc. Because the metal is above the salt, it's going to happen. So this reaction is going to happen. Because the zinc wants to become oxidized big time, because it's high up there. Yeah, we're just going by this. So in this case, the salt is below the metal. The metal is zinc. That means a reaction happens. So now we can rewrite this. All right. And what was the spectator ion? We have to put the spectator ion back in. Look at spectator ion, the Cl. Right? The Cl doesn't do anything. It's just carried along. So the original Cl was part of the acid. So the last step is put the spectator ion back in. So frequently, I'll also ask for you to identify the spectator ion. So just keep an eye on what's the spectator ion here. And notice there are no spectator ions on the activity chart. So anything not on the activity chart is going to be a spectator ion. Want to do another one? Oh, let's see now. If you live near the salt water and have a boat, your boat is frequently aluminum. Aluminum metal. Not all the time, but most smaller boats, like 24 foot and down, are either fiberglass or aluminum. Frequently, though, they're aluminum, especially if it's a utility boat, like a fishing boat or a commercial fisherman or something like that. Usually they're aluminum, not fiberglass. Aluminum is more durable. Okay, and if you have anything metal other than aluminum bolted to your boat, you have to insulate it with something like plastic. So let's say you didn't do that. You're a newbie and you didn't realize you had to insulate non-aluminum metal that's attached to your aluminum boat. Let's say you're attaching you were desperate and you needed to have a bolt and it happened to be an iron bolt. What's going to happen to your iron bolt? Is it going to be turned into iron +2, or is it going to stay iron and the aluminum is going to be converted to aluminum +3? So again, you look on your activity chart for aluminum and iron. Okay, here's aluminum, and here is iron. Which one wants to become oxidized more than the other? The aluminum or the iron? Which is higher? Aluminum. So that wants to become oxidized. So what's going to happen is when you take your iron bolt and you attach it to that aluminum hull, the aluminum is going to corrode, not the iron. Because aluminum wants to be oxidized more than the iron wants to be oxidized because it's higher. No. It'll stay nice and shiny. Because what's happening is the aluminum is pulling off everything. Because it wants to become oxidized more than the iron does. So the iron won't oxidize. It'll stay iron, and the aluminum will start to corrode. So your hole will get bigger and bigger. So you want to choose something where the aluminum is higher. And if you find a metal, like a metal fastener where, let's say it's magnesium right above it. So if you chose a magnesium bolt, the bolt is now going to dissolve and leave your aluminum hull intact because the magnesium then is going to want to be oxidized. Yeah. Separate. Now, when you're in salt water, there's a process called electrolytic corrosion, which is what we just did. So some people will buy a chunk of magnesium and bolt it to their aluminum hull. And the magnesium wants to be oxidized more so than the aluminum. So the aluminum will stay fine, and then magnesium will gradually dissolve away. And it's called a sacrificial plate. And it only works because it's salt water. In fresh water, you don't need one, because the salt acts as a conductor of electrons being transferred, where in fresh water, it doesn't happen as well. And this is a reality. Aluminum boats in like the Bay Area that is exposed to salt air, or actually on the salt water, they'll have sacrificial blocks bolted to them. Very common. Most aluminum boats that are typically used in salt water come with it already. You can also retrofit your boat. Okay, so that's a really nice application of this whole bit. We're picking suitable metals that contact each other. Now, if you have an insulator between the two of them where electrons are not allowed to go through the insulator, nothing will happen. But if you're forced to have metal against metal, you need to look at this activity chart and see which one's going to dissolve and which one's not going to dissolve. And you want to pick an appropriate combination. Okay, so that's it for today.